Our farthest spacecraft has been traveling for nearly 50 years, yet it hasn't even come close to the edge of what we call our cosmic neighborhood. On September 5th, 1977, Voyager 1 launched from Cape Canaveral. Since then, it has never stopped for a single moment. Today, the spacecraft sits more than 168 astronomical units from the Sun. 1 astronomical unit equals the distance from Earth to the Sun, roughly 150 million kilometers. Voyager 1 passed all the planets long ago and traveled beyond the main part of the Kuiper Belt, but it still has about 300 years to reach the inner edge of the structure we're about to discuss. Crossing that boundary will take another 30,000 years. 30,000 years. For comparison, all recorded human history spans only 5,000 years. Enough time to repeat the entire timeline 6 times, from the earliest Sumerian tablets to now. This structure is called the Oort Cloud, a hypothetical, vast region at the very edges of our solar system. And here's where things get strange. No one has ever seen it. No telescope has ever captured it directly. No probe has reached it, and none will in the foreseeable future. Yet most astrophysicists accept its existence as a working fact, not as a wild guess or a footnote assumption, but as the best explanation for a whole set of observed phenomena. I struggled to wrap my head around this. How can you be sure about something that's fundamentally impossible to see? This isn't just a distant galaxy we haven't photographed in high resolution yet. It's an object physically beyond what our technology can reach. And still, scientists nod and say, yes, it's out there.
Wait a second, haven't the Voyager spacecraft left the solar system? That's what all the headlines said. I thought so too, but that's not exactly true. In fact, if we're being precise, it's completely false. What the Voyagers crossed is the boundary of the heliosphere, the region dominated by the solar wind, streams of charged particles from our star. Beyond that lies the interstellar medium. News outlets wrote, left the solar system, and sure, it sounds impressive, but gravity is what truly defines what belongs where. And by that measure, both Voyagers are still deeply inside the solar system. They haven't even left the scattered disk, let alone reached the Oort cloud. Put simply, Voyager has crossed the threshold of the solar wind, but it still has a long way to go before it escapes the sun's gravitational pull. The difference between these two boundaries is like the difference between stepping out of your apartment and leaving the city. Opening your building's front door is one thing. Reaching the city limits is something else entirely. The scale is incomparable. Here's what really grabbed me when I started digging into this topic. The farthest object in the solar system we've ever observed directly lies about 132 astronomical units away. Meanwhile, estimates place the inner edge of the Oort cloud somewhere between 2,000 and 5,000 astronomical units. That means the gap between what we can actually see and what we believe exists stretches tens of times farther. But this isn't blind faith, it's a scientific investigation. Researchers have indirect evidence, solid, testable, repeatable clues connected to objects that arrive from this hidden zone. And these objects behave in very specific ways. What exactly are these clues? Why do they convince us so strongly? And what picture do they paint? That's what we're about to uncover. But first, we need to understand what we actually know about the space between the planets and that elusive outer boundary. The solar system isn't just 8 planets in empty space. Out there, in our cosmic backyard, there's something more. And that something sets the scale we need for comparison. Between Mars and Jupiter stretches the main asteroid belt, millions of rocky fragments left over from a planet that never formed. Beyond that, along Jupiter's orbit, 2 points of gravitational balance hold what we call the Trojan asteroids, thousands of massive rocks leading and trailing the gas giant like a convoy. And past Neptune's orbit, from about 30 to 50 astronomical units from the Sun, lies the Kuiper Belt, a ring of icy bodies that includes Pluto, Makemake, Haumea, and hundreds of thousands of other objects coated in frozen methane and nitrogen. These are well-charted neighborhoods, places we can see, catalog, and photograph.
But the map doesn't end at the Kuiper Belt. This is where the scattered disk begins, a region with far fewer icy bodies, stretching out as far as 1,000 astronomical units, according to estimates. It's not a ring anymore, but more like a blurred trail. Objects here follow elongated, chaotic orbits, thinning out the farther they get from the Sun. The scattered disk marks the last frontier where we can even hope to catch a glimpse of anything. And here lies the biggest challenge of scale. Because beyond the scattered disk, the Oort cloud is thought to begin. Its inner edge sits somewhere between 2,000 and 5,000 astronomical units. The outer boundary could extend as far as 100 to 200,000. To wrap your mind around these numbers, you need to take a mental leap. Let's start from the Sun. 1 astronomical unit equals the distance to Earth, about 150 million kilometers. Neptune lies 30 of these units away. The edge of the Kuiper Belt sits at 50. So far, all these distances fit neatly on a ruler you could draw on a sheet of paper. The scattered disk stretches out to 1,000 units. That calls for a bigger sheet. Now the inner edge of the Oort cloud begins at 2,000 units. Imagine fitting the entire Kuiper Belt, the full extent of what we know about the icy outer reaches, into just the first centimeter of that ruler, then measuring another 40 centimeters before you even reach the start of the Oort cloud. And that's only the beginning. The outer edge extends 200,000 astronomical units. That's roughly half the distance to the nearest star, Proxima Centauri. The ruler runs out. The table runs out. The room runs out. All the objects we just mentioned, the asteroid belt, the Trojan asteroids, the Kuiper Belt, the scattered disk, sit neatly in a single plane. Like a plate, a flat disk spinning around the Sun. But out at the very edge, where the Oort cloud should be, that plane just disappears. Models predict the Oort cloud isn't a ring or a disk. It's a sphere, a vast three-dimensional shell that wraps around the entire solar system like a giant shell. But if it's so enormous, why can't we see it? The answer comes down to 3 factors, and each one works against us. The first is distance. Objects in the Oort cloud lie so far away that the sunlight reaching them, bouncing off, and returning to us has to travel a staggering journey. And light intensity drops with the square of the distance. Think of it like a flashlight. If you step back just 2 feet from a wall, the light spot becomes 4 times dimmer. Not twice, 4 times. But here's the catch. The light has to make the trip twice, from the Sun to the object, then back to our telescope. That means brightness falls off with the distance raised to the 4th power. An object 5,000 astronomical units away reflects 10 trillion times less light than one of the same size orbiting Neptune. 10 trillion. This isn't just a little dimmer, it's almost nothing. The second reason is motion, or rather the lack of it. Astronomers spot objects in the solar system by tracking how they shift against the backdrop of fixed stars. Take a photo today, take another tomorrow. If the point moves, it's not a star. But the farther an object is, the slower it creeps across the sky. At distances of thousands of astronomical units, its apparent motion becomes so faint that astronomers need months, even years of continuous observation of the same patch of sky to detect it. Meanwhile, the object itself is a tiny, icy chunk about 5 kilometers across, so dim it nearly blends into the void. The third reason, and in my opinion the most revealing, is the story of Planet 9. Planet 9 is a hypothetical world. If it exists, it should be several times more massive than Earth, not some icy pebble, a full-fledged planet. Calculations place it roughly 400 astronomical units away. That's closer than the inner edge of the Oort cloud by a factor of 5 to 12, and it's larger than any object we expect to find out there. You'd think spotting something like that would be easier than finding a 5-kilometer ice chunk, but we haven't been able to find it. The world's top survey telescopes have been scanning the sky for years, and the result? Nothing. If an entire planet can hide from us at 400 astronomical units, what hope do we have of spotting ice boulders at 5,000, or even 50,000? The scale of the problem becomes clear. Our instruments can capture the light of galaxies billions of light years away, yet they go blind when it comes to small, dark bodies in our own cosmic backyard. Here's a clear point of reference. The most distant object in the solar system we've ever observed directly is 2018 AG37. Astronomers spotted it at 132 astronomical units away. 132. Meanwhile, the inner edge of the cloud we're searching for starts at 2,000 astronomical units. That means there's a 15-fold gap between our absolute farthest sight and the first boundary of what we're trying to find. Imagine a flashlight illuminating just the first 2 meters of a path, while the house you need stands 30 meters ahead, completely shrouded in darkness. This creates a strange situation. Telescopes can see galaxies at the very edge of the observable universe, because they glow brightly on their own. But a 10-kilometer chunk of ice drifting in the darkness between stars doesn't shine by itself. It only reflects light. And out there, there's barely anything to reflect. Sunlight that far away is no brighter than a distant star. Yet scientists remain confident the cloud exists. Not because of photographs, there aren't any. Not from radar signals, those wouldn't reach that far. Their certainty comes from something else. From the objects that come flying in from that very place. They emerge from the darkness, briefly flare up near the sun, and then vanish back into the void. Each time, they carry clues about where they came from. We're used to comets, a glowing tail streaking across the night sky, stunning photos, a touch of romance. But from a physics standpoint, their existence today is a complete anomaly. They simply shouldn't be here. To understand why, we first need to figure out what a comet really is. For a long time, people had no clue. For centuries, comets weren't seen as cosmic objects at all. Instead, they were thought to be atmospheric phenomena, something like unusual clouds or glows in the upper layers of the air. Aristotle, back in the 4th century before our time, insisted that comets were born in Earth's atmosphere, like vapors rising up. That idea held strong for more than 1,500 years. It wasn't until the 16th century that the Danish astronomer Tycho Brahe measured the parallax of the comet of 1577 and proved it was farther away than the moon. This wasn't a weather event. It was an object in space, an object moving between the planets. When astronomers began tracking these objects systematically, they discovered something fascinating. Comets fall into 2 fundamentally different categories. Short-period comets return to the sun more often than once every 200 years. Take Halley's Comet, for example. It appears every 75 to 76 years. Its orbit is clear, predictable, and stays well within the solar system. Then there are long-period comets, which take more than 200 years to complete an orbit. Some follow such stretched-out ellipses that a single trip around the sun lasts tens of thousands of years. They come from deep darkness, sweep past, and then vanish back into the void. For a long time, people thought comets were just dirty snowballs. A core of ice mixed with dust and rock. It's a nice metaphor, but not quite right. Modern models tell a different story. Ice makes up only about 20 to 30% of the comet's mass. The rest is rock, dust, and organic compounds. Simply put, a comet isn't a snowball smeared with dirt. It's a clump of dirt, just lightly soaked with ice. And here's where the problem begins. Every time this clump approaches the sun, the ice on its surface starts to evaporate. Not melt, it sublimates. It jumps straight from solid to gas. This gas carries dust particles away, forming a tail, that glowing stream we can see from Earth across millions of miles. But beauty comes at a cost. With each orbit, the comet loses a part of itself, layer by layer, pass after pass. It's like dropping an ice cube onto a scorching skillet. It never comes back the same. But evaporation isn't the only threat. Jupiter's gravity can capture a comet and reshape its orbit. It can speed it up so much that the comet escapes the solar system forever. Or it can hurl it straight into a planet, like what happened with comet Shoemaker-Levy 9 in 1994, when 21 fragments of its core slammed into Jupiter's atmosphere one after another. The impact scars were as big as Earth. Evaporation near the sun, collision with a planet, a gravitational slingshot out of the system. 3 ways to die, and not a single way to be reborn. Where does this lead us? To simple arithmetic. The solar system is 4.6 billion years old. An active comet that regularly approaches the sun lives only a blink in cosmic terms. Thousands, maybe tens of thousands of years. Even if we round that up generously, it's just a fraction of a percent of the system's age. All the comets that existed when the planets formed should have long since vaporized, broken apart, or flown away. Yet, they keep arriving. Every year, astronomers spot new, long-period comets entering the inner solar system for the first time, at least for the first time in millions of years. They couldn't have been sitting here all along. That means they must have come from somewhere else recently, from a place where time flows differently, where there's no scorching sunlight, no planetary traps, nothing to destroy them. Here lies the mystery. Comets exist, though they really shouldn't. Back in the 19th century, when astronomers first tried to precisely track their paths, the answers they found only deepened the confusion. The answer turned out to be deceptively simple. 19th century astronomers aimed their telescopes at long-period comets and calculated their paths, then breathed a sigh of relief. The orbits came out parabolic, and some even hyperbolic. Their eccentricity was 1 or greater. That meant one thing. These comets weren't from around here. They came from interstellar space, zipped past the sun, and disappeared back into the darkness. No mystery about their origin, just passing visitors, nothing more. Let's pause for a moment, because we can't move forward without understanding one key term. Eccentricity, simply put, is a measure of how stretched out an orbit is. When eccentricity is 0, the orbit is a perfect circle. The closer it gets to 1, the more elongated the ellipse becomes. But if eccentricity equals or exceeds 1, the orbit opens up. The object flies by once and never comes back. Imagine throwing a ball so hard it sails over a fence and rolls onto the next street. It won't return. Now, if eccentricity is just a bit less than 1, say 0.99, the orbit remains closed. The ball, though it takes a huge arc, will eventually come back. This is the crucial difference. Less than 1 means it's ours. 1 or more means it's a visitor. And here's where things get really fascinating. In the 20th century, as instruments became more precise and calculations more rigorous, an uncomfortable truth came to light. The very comets once thought to be visitors from beyond the stars were actually tracing closed elliptical orbits. Their eccentricity wasn't exactly 1, but just a bit less. 0.99, 0.998. Their paths stretched insanely far, tens of thousands of astronomical units from the sun, but they looped back. In other words, these comets belonged to the solar system. They always had. It was just the roughness of earlier measurements that kept this fact hidden. Here's the irony. When the instruments gave false readings, there was no problem. Comets were just visitors. Case closed. But as soon as astronomers learned to measure with greater precision, they created a puzzle for themselves. If comets belong to us, if they are gravitationally bound to the sun, then where do they come from? Why haven't they run out after 4.5 billion years? What is their source? The very accuracy meant to provide answers ended up raising a question that no one could solve for decades. One idea stood out for its elegance. What if, somewhere at the very edge of our solar system, a planet hides in the shadows? Not a small or modest one, a gas giant several times the mass of Jupiter, orbiting about 15,000 astronomical units from the sun. So far out that no telescope has ever spotted it. This hypothetical planet earned the name Tyche, after the Greek goddess of fortune. In ancient Greek, Tyche didn't just mean luck. It meant blind, unpredictable fate, a fitting name for an object that might steer the chaotic paths of comets. The reasoning was clear. Tyche, slowly orbiting on the outskirts, would occasionally tug icy bodies from their usual paths, flinging them toward the sun. One massive planet, and the mystery of comet showers would be solved. It was a beautiful theory, a testable theory. In 2009, the infrared observatory WISE launched into orbit. Its mission was ambitious, to map the entire sky in infrared light. A gas giant several times the mass of Jupiter, even from 15,000 astronomical units away, would emit enough heat for WISE to detect it. The observatory did its job. Scientists analyzed the data. There was no sign of a Tyche-like planet in our solar system. Not at 15,000, not at 26,000 astronomical units. Nowhere. The hypothesis that once neatly explained everything was shattered by infrared images. The comets are ours, not visitors from some distant world. And the giant shepherd planet that might have steered their orbits? It seems it simply doesn't exist. The two most obvious explanations had fallen apart. The investigation hit a dead end. But something in this data slipped through unnoticed. Take a closer look, not at individual comets, but at the entire spread of their orbits, the statistics, and a pattern emerges. A strange one. Too precise to be a coincidence. It took someone to think to look at it that way. 1932, Tartu, Estonia. Ernst Öpik, an astronomer known as a brilliant theorist, yet working far from the world's major observatories. That year, he published a paper exploring the fate of comets. His reasoning was simple. If comets break apart every time they near the sun, and the solar system is 4.5 billion years old, then there must be a reservoir supplying new ones. Öpik proposed this reservoir lies at the very edge of the system, a cloud of icy bodies too distant to see, but numerous enough to feed comet streams for billions of years. The idea was published. The idea was ignored. A small university, a small country, a looming war. If Öpik had worked in Leiden or Cambridge, we might be talking about the Öpik cloud today. But history had other plans. 18 years passed. In 1950, Dutch astronomer Jan Oort, by then one of the leading experts on the structure of the galaxy, the man who mapped the rotation of the Milky Way, tackled the same problem. He referenced Öpik, giving credit where it was due. But Oort took a different approach. While Öpik reasoned theoretically, Oort decided to crunch the numbers. He gathered data on the orbits of all the long-period comets known at the time, those that take hundreds, thousands, or even millions of years to complete one orbit around the sun. Then he created a histogram. On the horizontal axis, he plotted a value called the inverse of the orbit's semi-major axis. Simply put, this number shows how far the comet travels from the sun at its most distant point. The closer this value is to zero, the farther the comet ventures out. On the vertical axis, he plotted the number of comets with that value. And here, things get really interesting. The graph revealed a sharp peak. Not a scattered cloud of points, not a smooth curve, but a clear, distinct concentration. And this peak sat almost right at zero. What did that mean? It showed that the vast majority of long-period comets didn't come from random distances. They originated from the same region, tens of thousands of astronomical units away from the sun. To put that in perspective, Pluto orbits about 40 astronomical units out. But here, we're talking about distances 1,000 times greater. It's like Pluto is your backyard gate, and the source of these comets is a city on the opposite side of the country. But that's not all. The comets that made up this peak showed a striking pattern. Their orbits were almost parabolic, stretched out so far that they essentially had no return path. Each one was making its very first trip into the inner solar system. They weren't coming back from a previous pass. They were arriving for the first time. It's as if something knocked them off their usual route and hurled them toward the sun, where they had never been before. One comet like this might be a fluke, 10, a coincidence. But when most of these new comets trace back to the same origin, it's a clue. A structure emerging through the noise of the data, like a watermark seen when held to the light. Here's a common misconception we need to clear up. Many people imagine the Oort cloud as something like the asteroid belt, just farther out. A flat ring stretched out in the same plane where the planets orbit. But the data from Oort told a different story. He noticed a second key detail, the directions from which comets arrived. The asteroid belt and the Kuiper belt do lie roughly in the same plane, the plane of the ecliptic. If the source of comets was also flat, they would mostly come from that plane. Instead, long-period comets arrive from every direction, from above, below, sideways, evenly from all points in the sky. And the only shape that surrounds an object evenly from all sides? A sphere. Not a disk, not a ring, a sphere. Two key factors, distance and direction, transformed a dry chart with an unremarkable horizontal axis into a vivid image of a colossal structure. A gigantic, spherical swarm of icy objects enveloping the entire solar system, tens of thousands of astronomical units away. No one had ever seen it. Not a single telescope had spotted individual bodies at that distance. Yet the math insisted it was there. Oort had, in effect, glimpsed the invisible, not through a lens, but as a column on a histogram. Still, one detail refused to be ignored. The cloud explained where comets come from, but where did the cloud itself come from? These icy bodies, so far out that the sun looks like just another bright star among thousands, how did they get there? They couldn't have formed in place. That far from the star, the material in the original disk was too sparse to clump into anything. So something must have thrown them out there. 4.5 billion years ago, a disk of gas and dust swirled around the young sun. Near the star, it blazed hot. At the edges, it froze into icy cold. Particles collided, stuck together, and grew, starting as tiny grains, then stones, then the seeds of planets. In the zone where temperatures allowed water to freeze, icy chunks gained mass faster than anywhere else. It was here, between 4 and 30 astronomical units from the sun, that the bodies destined to become comets took shape. They didn't form on the outskirts of the solar system. They formed right next to the planets that would become giants. And that posed a problem. Jupiter gained mass first, 318 times the mass of Earth, in compressed gas and metallic hydrogen. Saturn, Uranus, and Neptune followed close behind. Each of them became a gravitational trap, but not the kind that holds on. Instead, one that flings objects away. When a small icy body passed close enough to young Jupiter, it didn't fall in. The giant's gravity grabbed that chunk of ice, sped it up, spun it around, and then flung it outward, like a stone from a sling. This is the same principle engineers use today to accelerate interplanetary probes, the gravitational slingshot. A spacecraft approaches a planet, steals a bit of its orbital energy, and leaves moving faster than when it arrived. But instead of a single probe every few years, billions of icy fragments were launched continuously over hundreds of millions of years. Jupiter operated like a factory, churning out comets. Ejected bodies were sent into stretched elliptical orbits, far from the sun, reaching thousands or even tens of thousands of astronomical units away. But these orbits remained elongated. No matter how far a body drifted, it always came back eventually to the spot where it was thrown out, to the realm of the giant planets. Each return triggered a new maneuver, a fresh ejection, a new chance to be flung even farther or lost entirely in interstellar space. You might think this process would simply clear the system. Anything that didn't become a planet would be gone forever. Yet, at the farthest edges, another force came into play. The entire Milky Way galaxy, not just a single star, but its full mass, exerts tidal forces. These forces are gentle, barely noticeable, yet they act continuously over billions of years. Slowly, they began pulling the farthest point of the orbit, twisting its plane, and changing its tilt. Imagine someone turning a hoop ever so slowly, while a ball jumps through it. The ball still flies, but its path's ring gradually rotates through space. Alongside these galactic tides, random flybys from neighboring stars added small nudges, each one pushing the orbit in a different direction. Over billions of years, these tiny jolts accumulated. The elongated ellipses grew rounder. The orbit's closest point to the sun lifted, so the body stopped returning to the giant's zone. It got stuck on the outskirts forever. Meanwhile, the orbital plane, which once matched the disk's plane, twisted to a random angle. The result? Over 4 billion years, a flat stream of ejected icy bodies transformed into a spherical cloud. More precisely, two distinct structures. The inner region, stretching from 2,000 to 20,000 astronomical units, still holds a slight flattening, a faint echo of the original disk. Beyond that, starting around 20,000 astronomical units, lies a fully formed sphere, mixed so thoroughly that it's uniform. Two layers of the same system, frozen at different stages of blending. It's an elegant theory, a logical one, but it has one inconvenient detail. Calculations show that ejections from our own disk alone might not be enough. Estimates suggest the Oort cloud contains roughly 1 trillion objects larger than a kilometer. Tossing that much material away, relying on just 4 planets, pushes the limits of what's possible. And that's where an alternative hypothesis creeps in, one that sends a shiver down the spine. The Sun wasn't born alone. It formed inside a dense cluster of stars, dozens, maybe even hundreds of young stars packed within just fractions of a light year from each other. Each star had its own protoplanetary disk. Each had its own Jupiter-like planet, flinging icy bodies to the outskirts. In this crowded stellar nursery, where the gravitational fields of young stars tangled together, our Sun could easily capture material from its neighbors. An icy body, launched by a nearby star, would drift past the Sun and stay. Captured. Stolen. Some models suggest that as much as 80 to 90% of the objects in the Oort cloud didn't originate from our solar disk at all. They formed around other stars, in different protoplanetary systems, made from different material. Then the cluster gradually dispersed, the stars scattered, and the Sun carried its stolen bounty along. A cosmic heist committed 4.5 billion years ago. So, what exactly lies within this hidden vault? Mostly ice. Water ice, methane ice, ammonia ice. Frozen volatile substances, preserved at temperatures just a few degrees above absolute zero. But it's not just ice. In 2021, a meteor streaked across the Canadian sky. Its path pointed straight back to the Oort cloud. Analysis revealed it was a rocky object. Not icy, rocky. That means the outer edges of our solar system don't just hide frozen comets. They also conceal rocky fragments, pieces of stone that, by all logic, shouldn't even be there. There's also a hypothesis that sounds almost like science fiction, but rests on solid physics. If the young Sun could capture icy chunks from nearby stars, what stopped it from grabbing something bigger? Like a rogue planet, a world cast out from another star system, drifting alone through interstellar space. If the Sun caught such a planet with its gravity early on, it might have settled into a stable orbit somewhere deep within the Oort cloud. Dark, cold, invisible to every telescope we have today. A foreign planet living in our solar system. So we have a vast reservoir, 1 trillion objects frozen solid for billions of years on the distant edges of space. Stable, mixed up, and hidden. But every now and then, one of these icy bodies breaks loose from its remote orbit and begins a slow fall toward the Sun. Something pushes it, and that something doesn't come from inside the system. It comes from beyond, and it has a name. Actually, several names, because there are more triggers capable of shaking loose an icy block from its orbit, where it has slept for billions of years, than you might expect. But first, a question worth asking head-on. If the Oort cloud is stable, if its objects have been frozen in place on orbits unchanged since before even single-celled life existed on Earth, if this whole system hangs in delicate balance, then why do comets even break free? What disrupts a system that's held steady for 4.5 billion years? The answer begins with stars. Not ours, but others. The Milky Way is not a still picture. Its stars are constantly moving, and from time to time, one drifts close enough to the Sun for its gravity to reach the farthest edges of our solar system. Close enough, in cosmic terms, means about 1 to 2 light years. That's an immense distance by any earthly measure. But for objects in the Oort cloud, already a light year away from the Sun, it's like someone walking right past a house of cards. No direct hit, just a close pass, but enough to stir things up. The passing star's gravity doesn't yank comets out of the cloud. It works more subtly. It tweaks orbital parameters, nudging the eccentricity here, tilting the orbital plane a bit there. And that tiny shift is enough to send a body, which has orbited in a closed loop for billions of years, suddenly onto a new path, one that leads inward, toward the sun, toward warmth, toward the comet's glowing tail. Simply put, a star doesn't push a comet. It reshapes the path the comet was already following. According to calculations, these close encounters happen about once every 100,000 years. That might sound rare, but compared to the age of the solar system, it's fairly frequent. Here's the intriguing part. Passing stars aren't the main force at work. There's something much larger and, in my view, far more elegant at play. The tidal forces of the Milky Way itself. Our galaxy isn't just a single point or a uniform backdrop. It's a disk with a core and spiral arms, with mass distributed unevenly. All that mass, hundreds of billions of stars, clouds of gas, and dark matter, creates a gravitational gradient. The side of the Oort cloud closer to the galactic center feels a slightly stronger pull than the far side. The difference is tiny, but it's constant. This force doesn't act once every 100,000 years. It works every second, non-stop, throughout the entire history of our solar system. It's like a current in a river. A rock on the riverbed doesn't notice it for years, but a grain of sand resting at the very edge will eventually get swept away. Objects in the outer Oort cloud are just like those grains of sand. They cling to the sun barely, right at the edge of its gravitational pull. The galaxy's tidal forces slowly, patiently shuffle their orbits, and eventually, some begin to fall inward. Objects in the Oort cloud have their orbits thrown off by a few forces: the gravitational pull of passing stars, the tidal forces of the galaxy, and sometimes even stranger visitors. Rogue planets, ejected from distant star systems and drifting through interstellar space, can also disrupt this fragile balance, if they pass close enough. Then there are colossal molecular clouds, vast clusters of gas and dust weighing tens of thousands of suns that the solar system periodically crosses on its journey around the galactic center. Each crossing isn't a collision, but a gentle gravitational handshake that sends several comets to new addresses. We face a strange picture. 1 trillion objects hang on the edge of the system in perfect balance. But that balance is an illusion. It lasts only until the next close encounter with a star, until the next orbit around the galactic center, until the next subtle gust we can't even detect. Then, somewhere 70,000 astronomical units from the sun, a tiny icy fragment slips off its orbit. Not by accident. It happens because our system has never been alone. It's part of a structure vastly larger than itself, and that structure reminds us of its presence from time to time. If all this holds true, then the reservoir has been found, the replenishing mechanism explained, and the trigger described. But one question remains unsettling. What if clouds like this surround not just our sun? And if they do, is there any chance we could detect them? Let's bring it all together. The chain we've built, link by link. Long-period comets are real. We observe them every year. Several of them rush into the inner solar system, following orbits that carry them hundreds of thousands of astronomical units away from the sun. Some take millions of years to complete one orbit. That means they couldn't have formed nearby. They need a reservoir, somewhere distant, cold, and stable. In 1950, Jan Oort pointed to the only place these comets could come from: a spherical shell located between 20 and 100,000 astronomical units out. The formation process makes sense. Young giant planets flung icy bodies to the system's outskirts, while the galaxy's tidal forces and passing stars locked them into steady orbits. The trigger is clear too. Those same stars, the galactic tides, and molecular clouds occasionally nudge individual objects back toward the sun. That paradox we started with, why comets still exist if they should have long since evaporated, finally finds an answer. To this day, the hypothesis of the Oort cloud remains the best explanation for the full range of comet observations. Not just one of the explanations, the best one. But here's an important caveat, and it matters. The Oort cloud has never been directly observed. No telescope has ever captured an object that clearly belongs to this distant structure. Not a single probe has reached its inner edge. Even Voyager 1, the farthest human-made object, has traveled just over 160 astronomical units in 46 years. It would still take about 300 more years to reach the Oort cloud's inner boundary. Without direct observation, we can't claim its existence with absolute certainty. This isn't a weakness, it's honesty. The word hypothesis often gets mistaken for uncertainty, but in science, a hypothesis isn't a timid guess. The Greek root hypothesis literally means foundation, something laid down at the base. And this foundation isn't the hunch of one person, it's the convergence of independent lines of evidence. The orbits of comets, their isotopic makeup, the distribution of their farthest points from the sun, the dynamics of planetary migration. Each comes from a different field, yet all point to the same conclusion. Any competing hypothesis must offer a different explanation for where long-period comets come from and the quirks of their orbits. Not just one fact, but all of them at once. It has to explain why comets approach from every direction, why their farthest points cluster at certain distances, why the makeup of their ices suggests they formed near the sun, not in interstellar space. The bar to disprove this isn't a single counter-argument. It's a complete alternative picture. So far, that picture doesn't exist. Now, let's take a step back, or rather, a step outward. Our sun is a yellow dwarf star. There are about 10 billion of these scattered across the Milky Way. Many of them host planetary systems with gas giants, and as we've seen, gas giants act like cosmic slingshots, flinging icy bodies to the distant outskirts. So it makes sense to assume that other star systems like ours also have their own versions of the Oort cloud. The Oort cloud is probably not a quirk unique to our system. It's more like a standard architectural feature, like the foundation of a building, invisible from the outside but essential to its stability. The problem is, spotting someone else's Oort cloud is even harder than detecting our own. Objects just a few kilometers across, light years away, are far beyond the reach of any telescope. But there is one idea, almost crazy, and that's exactly why it deserves our attention. The cosmic microwave background is the faint microwave glow left over from the first few 100,000 years after the Big Bang. Its temperature measures 2.725 degrees above absolute zero. This background is almost perfectly uniform across the entire sky. Almost, but not quite. Scientists have proposed a way to hunt for exo-Oort clouds by spotting the tiny distortions these cold, vast structures could imprint on this ancient radiation. In simple terms, trillions of icy bodies orbiting a distant star, gathered into a sphere a light year across, might cast a subtle shadow on the oldest light in the universe. That shadow would be microscopic, barely measurable, but, in theory, detectable. So far, this remains a calculation. We don't yet have instruments sensitive enough to find it. But the very fact that this method exists means one thing. The question has moved from philosophical speculation into the realm of an engineering challenge. And engineering challenges? They usually get solved. Sometimes in 10 years. Sometimes in 50. Arthur Eddington once said, "Don't trust observational results too much until theory confirms them." He was joking. Sort of. When it comes to the Oort cloud, the theory is solid. The logic fits perfectly. Every piece of the puzzle falls into place. Now all that remains is confirmation, and that confirmation will probably not come as a photo of a distant icy object. Instead, it might emerge as a statistical shadow on the map of the cosmic microwave background, or in data from a probe that hasn't even been designed yet. We started with a simple question. Where do comets come from if they can't last forever? The answer took us to the edge of the solar system, where the sun's gravity barely holds on, and the galaxy's pull begins to reach in. It turns out that edge is not empty. It's an archive, a 4.5 billion-year-old storage of cosmic debris. And every so often, under the influence of distant stars, it sends a package hurtling toward the inner system. We see it as a comet, a bright tail streaking across the night sky. But in truth, it's a message from the edge, from where our home ends and everything else begins.